A powerful seismic jolt has just struck one of the most tectonically active corridors on Earth, raising immediate questions about what exactly unfolded beneath the Southwest Pacific and what it signals for the region ahead. How does a quake of this scale originate so deep below the surface, far from where the most destructive shaking usually begins? Why does an event occurring more than 120 kilometers beneath the seafloor still manage to send tremors across island chains? And in a region that has already endured repeated major earthquakes over the past century, does this latest rupture fit an expected pattern or hint at a shifting tectonic balance? At 8:44 and 13 seconds in the morning Coordinated Universal Time on March 30, 2026, a magnitude 7.3 earthquake was recorded approximately 48 kilometers east-northeast of Luganville, a key urban center on the island of Espiritu Santo in Vanuatu. The hypercenter was calculated at a depth of about 121.3 kilometers, placing it well within what seismologists classify as the intermediate depth range. Its coordinates, near 15.3 degrees south latitude and 167.5 degrees east longitude, position it squarely within the convergent boundary where the Australia Plate descends beneath the Pacific Plate. This segment of the Pacific Basin is defined by constant motion, though rarely visible at the surface in real time. The Australia Plate is advancing east-northeastward at roughly 80 millimeters per year relative to the Pacific Plate. That incremental motion, measured annually in millimeters, accumulates strain across geological timescales until it is abruptly released in the form of earthquakes. The New Hebrides Trench, lying about 90 kilometers west of the epicenter, marks the surface expression of this ongoing subduction process. It is here the dense oceanic lithosphere bends downward and sinks into the mantle, carrying with it not just rock but enormous mechanical stress. The earthquake's mechanism indicates oblique thrust faulting, a combination of compressional and lateral motion. Moment tensor solutions suggest rupture along either a north-northwest striking, moderately dipping fault plane or a south-southwest striking, steeply dipping alternative. In both interpretations, the movement reflects the complex geometry of a subducting slab that is neither perfectly planar nor uniform in composition. Instead, it is fractured, warped, and internally stressed as it descends into higher pressure, higher temperature conditions. Unlike shallow focus earthquakes that rupture near the surface and often produce intense localized destruction, intermediate depth earthquakes distribute their energy differently. At depths between 70 and 300 kilometers, the surrounding rock behaves under conditions that suppress the kind of brittle fracture seen closer to the surface. Yet these earthquakes still occur, driven by mechanisms that may include dehydration reactions within the subducting slab, mineral phase transformations, or shear instabilities caused by internal stress concentrations. The result is a seismic event that can radiate energy over vast distances, even if its surface expression appears less catastrophic directly above the source. In the case of this magnitude 7.3 event, the depth likely moderated the intensity of ground shaking in immediate proximity to the epicenter. However, the same depth also enabled seismic waves to travel efficiently through the Earth's interior, potentially allowing the quake to be felt across a wide swathe of the Southwest Pacific. Communities separated by hundreds of kilometers may have experienced prolonged but less violent shaking, a hallmark of deeper seismic sources. Vanuatu's seismic history provides important context for interpreting this event. Over the past century, 19 earthquakes of magnitude 7 or greater have occurred within 150 kilometers of this latest rupture. This frequency underscores the region's classification as a high seismicity zone, where large earthquakes are not anomalies but recurring features of the tectonic system. The largest recorded in this vicinity, a magnitude 7.7 event in May 1965, occurred approximately 75 kilometers to the north-northwest of the current epicenter. That earlier earthquake, like the present one, was linked to the same subduction dynamics that define the New Hebrides arc. Espiritu Santo, the largest island in Vanuatu, sits within this active tectonic framework. Its proximity to the trench and the descending slab places it in a position where seismic waves from both shallow and deep earthquakes can converge. The island's geological structure, composed of uplifted volcanic and sedimentary formations, can influence how shaking is amplified or attenuated across different manatee. Coastal plains, coral terraces, and mountainous interiors each respond differently to incoming seismic energy, creating a patchwork of ground motion intensities even within relatively short distances. The timing and depth of the earthquake also raise considerations regarding tsunami potential. Typically, the most dangerous tsunami-genic earthquakes are shallow, involving significant vertical displacement of the seafloor. In contrast, intermediate-depth earthquakes like this one are less likely to generate large tsunamis because the rupture occurs too deep to directly displace the ocean floor in a substantial way. Nonetheless, initial assessments in the immediate aftermath would focus on confirming whether any secondary processes, such as submarine landslides, might have been triggered. The structural complexity of the subducting Australia plate plays a central role in understanding why earthquakes occur at these depths. As the slab descends, it carries water-rich minerals into the mantle. Under increasing pressure and temperature, these minerals undergo dehydration, releasing fluids that can weaken surrounding rock and facilitate sudden slip. Additionally, changes in mineral structure, such as the transformation of olivine into denser phases, can create internal stresses that contribute to seismic rupture. These processes operate far below the surface, invisible but measurable through seismic data. Another defining feature of intermediate-depth earthquakes is their ability to illuminate the geometry of the subducted slab. By analyzing the distribution of aftershocks and the orientation of the rupture plane, seismologists can map the contours of the slab as it bends and twists beneath the overriding plate. In regions like Vanuatu, where the subduction zone exhibits curvature and segmentation, each significant earthquake adds another data point to an evolving three-dimensional model of the Earth's interior. The energy released by a magnitude 7.3 earthquake is substantial, equivalent to several 100 million tons of explosive force. Yet that energy is not uniformly distributed. Some is absorbed by the surrounding rock, some is converted into heat, and some propagates outward as seismic waves. The depth of this event means that a significant portion of the energy traveled through the mantle before reaching the surface, undergoing attenuation and dispersion along the way. This process reduces peak ground acceleration near the epicenter, but extends the reach of perceptible shaking. Regional infrastructure and building practices also influence how such an earthquake is experienced. In areas where structures are designed to withstand seismic forces, even moderate shaking may result in minimal damage. In contrast, regions with less resilient construction may experience more pronounced impacts, even from deeper earthquakes. The interplay between seismic source characteristics and local conditions ultimately determines the observed effects on the ground. Communication networks and seismic monitoring systems in the Pacific have improved significantly over recent decades, enabling rapid detection and characterization of earthquakes like this one. Within minutes of the rupture, data from global and regional seismograph networks would have been analyzed to determine the earthquake's magnitude, depth, and location. This information is critical for issuing alerts, assessing potential hazards, and guiding emergency response efforts. Despite these advancements, the fundamental processes driving such earthquakes remain rooted in geological timescales. The steady convergence of tectonic plates, measured in millimeters per year, continues unabated. Each earthquake represents a momentary release of accumulated strain, but not a cessation of the underlying forces. In Vanuatu, as in other subduction zones around the world, the cycle of stress accumulation and release is ongoing. The distribution of past earthquakes in the region suggests that stress is not released uniformly along the plate boundary. Instead, it is partitioned across different segments and depths, leading to a complex pattern of seismicity. Some areas may experience clusters of activity, while others remain relatively quiet for extended periods before producing larger events. Understanding these patterns requires integrating seismic data with geological and geophysical observations, including bathymetric mapping, GPS measurements, and studies of plate motion. The March 30 event fits within this broader context as one of many significant earthquakes that have occurred along the Vanuatu arc. Its intermediate depth distinguishes it from the more hazardous, shallow megathrust earthquakes, but it also provides valuable insight into the behavior of the subducting slab. By examining the characteristics of this earthquake, its location, mechanism, and depth, scientists can refine models of how stress is distributed and released within the Earth's interior. As seismic waves from the earthquake dissipate and aftershocks begin to unfold, attention turns to the evolving pattern of activity in the region. Aftershocks, typically smaller in magnitude, occur as the crust and upper mantle adjust to the changes in stress caused by the main shock. Their distribution can reveal the extent of the rupture zone and highlight areas where stress has been transferred. In the hours following the earthquake, data continues to accumulate from monitoring stations across the Pacific. Each waveform contributes to a more detailed understanding of the event. From the initial rupture to the propagation of seismic energy through the Earth, this continuous stream of information forms the basis for ongoing analysis, shaping both immediate assessments and longer-term interpretations of tectonic behavior in the region. The broader implications of this earthquake extend beyond the immediate vicinity of Vanuatu. Subduction zones around the world share similar processes, and insights gained from one region can inform understanding in others. Intermediate depth earthquakes, while less visible in their impacts, are key to unraveling the dynamics of subducting slabs and the conditions under which they deform and fail. Even as the immediate effects of the quake are being evaluated, the underlying tectonic forces remain in motion. The Australia Plate continues its gradual descent beneath the Pacific Plate, carrying with it the potential for future seismic events. Each earthquake is a reminder of this ongoing process, a brief but powerful expression of forces that operate far beyond human timescales. In the hours following the magnitude 7.3 earthquake, attention shifted from the initial rupture to the sequence of aftershocks that began to unfold beneath the Southwest Pacific. These smaller events, while expected, are critical for mapping how stress redistributed through the subducting slab. Early seismic readings indicated a scattered but coherent pattern of aftershocks extending along a north-northwest to south-southeast trend, consistent with one of the fault plane solutions identified in the main shock analysis. This alignment provides a clearer picture of the rupture geometry, suggesting that the earthquake propagated along a defined section of the descending Australia Plate, rather than dispersing across a broad, undefined area. Most of these aftershocks remained below magnitude 6, with many occurring at depths comparable to or slightly shallower than the main shock's approximate depth of 121 kilometers or about 75 miles beneath the surface. This clustering within a relatively narrow depth band reinforces the interpretation that the deformation is confined within the subducted slab itself rather than along the plate interface closer to the ocean floor. The distinction matters because it points to internal slab processes, such as mineral transformations or localized weakening, as the primary drivers of the seismic sequence. The spatial distribution of aftershocks also reveals how stress has been transferred to adjacent sections of the slab. Areas immediately surrounding the rupture zone experienced a temporary increase in stress, triggering additional seismic events as the rocks adjusted to the new mechanical equilibrium. Conversely, portions of the fault that slipped during the main shock may now be in a state of reduced stress, at least in the short term. This redistribution is neither uniform nor predictable in detail, but patterns observed in similar events suggest that aftershock activity will gradually taper off over days to weeks, with occasional larger events punctuating the sequence. One notable aspect of intermediate depth aftershock sequences is their ability to extend over broader regions compared to shallow events. Because seismic waves at these depths travel efficiently through the mantle, even smaller aftershocks can be detected across vast distances. Monitoring stations throughout the Pacific Basin would have recorded these signals, contributing to a high-resolution dataset that allows for precise relocation of each event. This level of detail is essential for constructing a three-dimensional model of the rupture zone and understanding how the slab is deforming at depth. The regional seismic patterns surrounding Vanuatu has long been characterized by a combination of shallow megathrust earthquakes near the trench and deeper events within the subducting plate. The March 30 earthquake fits squarely into the latter category, but its occurrence does not exist in isolation. Instead, it forms part of a continuous sequence of stress accumulation and release that spans decades, if not centuries. Historical records show that clusters of large earthquakes in this region can occur within relatively short intervals, followed by quieter periods where strain builds silently beneath the surface. This raises an important consideration regarding whether the recent earthquake has altered the likelihood of additional large events in the near term. While it is not possible to predict specific earthquakes, the redistribution of stress following a magnitude 7.3 event can influence the timing of subsequent ruptures on nearby faults. Sections of the plate boundary that were already close to failure may have been nudged closer to their breaking point, while others may have been temporarily stabilized. The net effect depends on the complex interplay of forces within the region. Another factor to consider is the relationship between intermediate depth earthquakes and surface hazards. Although the depth of this event reduces the intensity of shaking directly above the epicenter, it does not eliminate risk entirely. Infrastructure across Vanuatu and neighboring island groups may still experience cumulative stress from repeated shaking, particularly if aftershocks persist. Buildings not designed for seismic resilience can develop structural weaknesses over time, even in the absence of a single highly damaging event. Ground response varies significantly depending on local geological conditions. Areas with unconsolidated sediments, such as coastal plains or river deltas, can amplify seismic waves, leading to stronger shaking than would be expected based solely on distance from the epicenter. In contrast, regions underlain by solid bedrock may experience more muted motion. This variability complicates efforts to assess damage potential in real time, as the same earthquake can produce markedly different effects across relatively short distances. In addition to ground shaking, attention remains focused on the marine environment surrounding the epicenter. While intermediate depth earthquakes are less likely to generate significant tsunamis, secondary effects cannot be entirely ruled out. Submarine slopes destabilized by seismic waves may fail, triggering localized disturbances in the water column. These events tend to be limited in scale compared to major tsunami events, but they can still pose risks to coastal communities, especially those in close proximity to potential landslide zones. The tectonic setting of Vanuatu further complicates the seismic picture. The subduction zone is not a simple linear boundary, but a curved and segmented system where the direction and angle of plate convergence vary along its length. This geometric complexity influences how stress is distributed and how earthquakes propagate. In some sections, the plate interface may be strongly coupled, accumulating significant strain before releasing it in large, shallow earthquakes. In others, deformation may be accommodated more gradually or at greater depths, as appears to be the case with the March 30 event. The rate of plate convergence, approximately 80 millimeters per year, or about 3.1 inches annually, is relatively high compared to many other subduction zones. This rapid motion contributes to the region's elevated level of seismic activity, as strain accumulates more quickly and must be released more frequently. Over time, this results in a dense record of earthquakes spanning a wide range of magnitudes and depths, each providing insight into the evolving dynamics of the system. Data collected from this earthquake will play a crucial role in refining models of subduction zone behavior. Seismologists will analyze waveforms to determine detailed rupture characteristics, including the duration of slip, the distribution of energy release, and the direction of fault movement. These parameters feed into simulations that attempt to recreate the event and assess how similar earthquakes might behave under slightly different conditions. Such models are essential for improving hazard assessments and informing preparedness strategies across the Pacific. Satellite-based measurements, including interferometric synthetic aperture radar, may also be employed to detect subtle surface deformations associated with the earthquake. Although the depth of the event limits the magnitude of surface displacement, even small changes can provide valuable clues about how the crust responded to the rupture. Combined with GPS data, these observations help scientists piece together a comprehensive picture of the event from the surface down to the depths of the mantle. The continuation of aftershock activity will be closely monitored in the coming days. While the frequency and magnitude of these events typically decrease over time, the possibility of a larger aftershock cannot be discounted. In many seismic sequences, the largest aftershock can reach a magnitude up to 1 unit lower than the main shock, meaning an event in the mid-6 range remains within the realm of possibility. Such an occurrence, while smaller than the initial earthquake, could still be widely felt and may exacerbate any existing structural vulnerabilities. If you found this detailed breakdown valuable and want to stay updated on major geological events around the world, make sure to like, share, and subscribe. Tap that hype icon to help this video reach a wider audience so more people can stay informed about the forces shaping our planet in real time.